All right, students, today we're going to do activity 1, experiment 1 in chapter 5. We're going to do several activities or several experiments in chapter 5, activity 1. And I just wanted to show you some of the materials that we're going to use. We're going to be using a PVC rectangle. We're going to be using several different shapes and sizes of copper. These are all made of copper, the same metal. This is just a tube sideways. We're going to be using a piece of brass, and we're going to be using a piece of aluminum. And so if you look in your workbooks at experiment number 1, it says the question is, how are mass and volume different? And so we're going to use two blocks with the same dimensions. We're going to be using the brass and the aluminum first. And we're going to be weighing them. Now if you can look at them, you can see that they are similar in shape and size, and that's what our requirements are. The mass of two blocks that have the same dimensions. Because they have the same dimensions, length times width times height, they also have the same volume. And what we're going to do is answer the question, how are mass and volume different? So I'm going to bring in the scale, and we are going to move the camera so that the scale can be read. And when you're using a scale, you always need to zero it out. So we're going to zero it out. Now it's reading 0. The first thing I'm going to measure, which goes under block 1, is the brass. Okay, so I want you to write down the mass of the brass, and unfortunately it's measuring in ounces, and we don't want ounces. We want grams. Okay? So record the mass of the brass in your table. And now I'm going to put the aluminum. Again, we got to zero it out. For some reason it's reading. We're going to put the aluminum the same, I should show you. It's the aluminum piece. It's the same dimensions as the brass, therefore the same volume as the brass. However, you can see that the mass is very different than the brass. Very different mass. So record those in table 1, and that is what we're going to do for experiment number 1. Now, the next part of experiment number 1 in step 3 is to record the material that make up each block in the table. And we're going to measure or take the dimensions of that. So I'm going to put this back up. I'm going to bring our samples back into view. Okay. And now what we're going to do is find the volume of blocks with the same mass. Okay. So we're looking at two blocks of about the same mass, but the problem is that they're going to be of different materials. So I've chosen to use this piece of copper and this piece of aluminum. And this piece of copper and aluminum have about the same mass. But now we are going to look at the volume. Okay, so I want to prove to you that these two objects have about the same mass. So we're looking at the aluminum, large aluminum piece, and the small copper piece. I'm going to put the aluminum piece on first, and you've already recorded that mass. Okay, and now the small copper piece. And they're very, very close, within 0.8 of a gram, so that's close enough for our purposes. So I just wanted to show you that we're using two very different looking pieces, these two pieces, but they have the same mass. Okay? So we're in table 2, volume of blocks with the same mass. We've got the copper, and now we're going to take the dimensions of the copper piece, which, if you can read on the ruler, the the length of the copper piece is 2.4. The width is 0.9, and the height is also 0.9 centimeters. You can see that this is kind of a square shape, so the length is one measurement, but the width and the height are the same measurement to make that square. So recording in the copper, you've got 2.5, 0.9, and 0.9. To find the volume of this piece of copper then, you're going to now take 2.5 times 0.9 times 0.9. Now, with significant figures, you're going to round that back. Well, you can just keep all the numbers for now. Okay? All right, now we're going to do the aluminum. We're going to take the length. And the length of the aluminum is 7.7 centimeters. And these have the same width and height. If I put those pieces together, you can see that they have the same width and height. So the width is 0.9 centimeters, and the height is 0.9 centimeters. So record the aluminum now, 7.7 centimeters for the length, 0.9 centimeters for the width, and 0.9 centimeters for the height. Multiply those to find the volume. Length times width times height is the volume. Okay, so now you have some different questions to answer regarding what we just did. So I want you to answer those questions. And we're going to move on then to experiment number 2, which tries to answer the question, is there a relationship between the mass and volume of material? So is there a relationship between the mass and volume of a material? In this case, we're going to again use the aluminum, and we're going to also use the copper. Okay? So in this case, we're going to look at the table on page 5-7 with experiment 2. It says masses and volumes for objects of the same material. We are going to take actually the copper, and we're going to measure the length, mass, and volume. We're going to measure the volume in different ways. Okay? All right. So the first thing we're going to do, we know the mass of this piece of copper, the small piece of copper, which was recorded in our last experiment. We know the length, we know the width, we know the height, and we're going to use those same measurements. You can take those same measurements from the table that we just used on page 5-3. So the length, remember, was 2.5, the width 0.9, the height 0.9. We'd multiply those numbers, we get the volume, and then the very last part on that column, you don't need to worry about the initial water volume, final water volume, and volume by displacement. In this case, we are finding the volume by length times width times height. So that final ratio of mass to volume is a calculation. Now, we're going to take that same piece of copper. We're going to take the same piece of copper, and instead of finding the volume through length times width times height, we're going to find the volume by liquid displacement. Okay? So I want you to, in your books, I want you to look at that second column that says Object 1, Liquid Displacement. Okay, so now here I am with water, and remember last time, well, once I did this and I used clear water, and now I decided I'm going to color the water. So I'm going to fill this graduated cylinder up to 20 milliliters. Okay, let's see if we can get a good read on that. And of course I used the wrong cylinder, so let me pour that into this cylinder, which I marked with a marker. Okay, let's see if we can see those numbers. Well, that second set of numbers is 20. So I have 20 milliliters. I'm going to pour a tiny bit out because it's a tiny bit over 20. I want 20. Okay, I have 20 milliliters of water in here. I'm going to add this piece of copper. Just like when you get in the bathtub, you notice that the level of water rises in the bathtub. The same thing happens when I add this little piece of copper to the graduated cylinder. The level of water rises. So I went from 20 milliliters, 20.0 milliliters, to 22.0 milliliters. So you're going to record that in your workbook where it says length times width times height. You just X that out. You don't even need to worry about that. Where it says, let's see if we can get this on the worksheet. So you're going to X out the length times width times height part. We started with 20. We ended with 22. The final is 2.0 milliliters. And now you're going to do your calculation again. It's the same piece of copper, so it's the same mass. You're going to take that mass divided by 2.0 milliliters this time, instead of divided by how many centimeters cubed. And you're going to get a number there. Okay, we're going to do this a third way. We're going to take now a piece of copper, but this piece of copper is irregularly shaped. Okay? This piece of copper is irregularly shaped. I've got my 20 mils of water again. Okay? We are going to use these cylinders. Okay? I could find the volume of these cylinders by some very complicated mathematical formulas, but it's much easier to use liquid displacement. Now remember, the whole point here is we're using a piece of copper each time. We use the small piece of copper, the regularly shaped piece of copper. We found its volume by length times width times height. We took the small piece of copper and we found its volume by liquid displacement. And now we're going to take irregularly shaped pieces of copper and we're again going to take the volume by liquid displacement. But first, we have to weigh them. So let's get our scale back. Okay, we got to zero out our scale. I'm going to show you that we're weighing the tubes of copper. And let's look at their mass is 23.0 grams. So record that. Object to liquid displacement, mass 23.0 grams. Now, again in your book, you're going to X out the length times width times height because we're not doing that. We're finding volume by liquid displacement this time. So, we're going to again start out with the 20.0 milliliters of water. We're going to slide these in gently. We don't want to splash the water. And we're going to see the level that it rose to this time. The level is, I'm trying to read it accurately here, about 22.4 milliliters. Okay, 22.4 milliliters. So the initial was 20, the final was 22.4. What volume did we displace? 2.4 milliliters. Now in this case, you're going to calculate that ratio of mass to volume by taking 23.0 grams, which was our mass, divided by our volume, and you're going to get a number there. Okay, so we've answered a couple of questions. Now let's go over to table 4, which involves densities and calculated values. And we've already figured out, we've already figured out a few of these. We figured out the brass in an earlier experiment. We figured out the copper in an earlier experiment. And those numbers should be already in your workbook. And now we're going to do the PVC. Okay? So we're going to do a calculated value for PVC. Do you remember the piece of PVC we started with? It looked like this. Okay? That's the PVC we started with. Just on the side of your workbook somewhere, I want you to record the mass of this PVC. Just put it anywhere along the margin out of the way. Okay, the mass is 16.9 grams. Okay, the mass is 16.9 grams. Now, how do we find the volume? We can find it one of two ways. We can either take liquid displacement, or we can do length times width times height. Okay, let's just do length times width times height. Let me turn on the other camera. So again, remember, when we find it, because this is a regularly shaped object, we can find the volume with mass times, or length times width times height. The length of this is 7.5 centimeters. The width is 1.8 centimeters. And because it's a square, again, the height, it's not 1.8, it's 1.3 centimeters. Okay, so the width and the height are 1.3 centimeters. Take those three numbers, the length times width times height, that will give you the volume. Take your mass, which we remember was 16.9 grams, divided by the volume, which you've calculated. And you should get a number similar to the one that is in your workbook. The one in your workbook is 1.4 grams per centimeters cubed. You should get a number very similar to that. Go ahead and do those calculations. All right, and our very last bit of data that we need to get is involving water. Okay, so what we're going to do is, and I don't want to use colored water for this because I don't know if the dye has a different density than the water, it might affect our results. So what we're going to do is we're going to get 10 milliliters of water. Okay, so I've got 10 milliliters of water. Very good. And I need an empty beaker. Okay. I did not bring a paper towel. Let me get a paper towel here. Okay. All right, so I've got an empty, dry beaker. I need to find the mass of the beaker. I've got the beaker on the scale. I'm going to weigh the beaker. The beaker weighs 67.9 grams. So in your table 5, where it says density of water, 67.9 grams. Now what I'm going to do is I'm going to add the 10 milliliters of water to the beaker. And the final mass is 77.6 grams. 77.6 grams. Find the mass of the water by dividing our first number by the second number, or by subtracting those two numbers. Okay? So we've got the mass of the water. What was the volume of the water? The The volume of the water was 10 milliliters. The volume of the water, we used 10 milliliters of water. Okay. The mass we figure out by subtracting those two numbers. To find the density of water, we're going to take the mass divided by the volume, or the grams divided by the milliliters. And one great thing about metrics, why we love metrics so much, is that 1 milliliter is actually equal to 1 cubic centimeter. So if you look on the fourth column in your workbook, the volume of water, 10 milliliters, which is also 10 centimeters cubed. Divide those two numbers, you should get a number very close to 1. The actual density of water is 1. We might be a tiny bit off because there might have been a drop left in the beaker or in the graduated cylinder. In fact, there are a few drops left that I didn't get into the beaker. Many, many reasons why we might be a tiny bit off, but the actual density of water is 1. Okay, and we just kind of proved it to ourselves, although our calculation is not exact. Okay, so if you look at the table, if you look at table 4, and you look at the numbers in table 4, let's look at those numbers. You see that acrylic has a density of 1.2. Would acrylic float in water if water has a density of 1? No, it would not. Okay. Would aluminum float in water? No, it would not. 2.7. Brass, copper. Would oak float in water? It has a density of 0.7, which is less than the density of water, which means, yes, it would float. In fact, the planet Saturn has a density less than water. If we had a bathtub big enough, we could put it in the bathtub and Saturn itself would float. It is not a very dense planet, whereas Earth, on the other hand, would sink, where our planet is much more dense. So when you think about density, we use water as our standard. Water has a density of 1. We compare everything to water. So you're going to be answering some questions. You're summarizing questions, and you're going to be looking at table 6, which talks about the densities of some liquids and gases. And so if you look at vegetable oil with the density of 0.93, okay, less than water, will it float in water? Yes. So when you think about Italian dressing, when you take it off the shelf and you see you have to shake it to mix everything up, it's because vinegar has a different density than the oil, and so those different density liquids settle in different spots in that container. So you can see some of the gases, like hydrogen, has a density of 0.000009. Very, very light. Okay? So I want you to answer your summarizing questions, and then the activity 1 homework is really excellent. You'll enjoy doing that. Thank you. See you next time.